So welcome everybody to the first lecture series for bladesmithing. For you that are not here, we're going to be using this when we go into do the high temperatures lab, so make sure to listen through the whole thing. I will repeat all questions so that everyone that's listening online can hear what we're talking about. Alright, so here's the summary of what we're going to be discussing today. We're going to go through the desirable properties for our materials and what we're going to be working with when it comes to bladesmithing. How we're going to obtain those desirable properties. Then we're going to go through phase diagrams and then a time temperature transition graph. Real quick, show of hands, how many of you guys have seen a phase diagram before? How many of you guys can read a phase diagram? Alright, cool, this number's shrinking. And how many of you guys have seen a time temperature transition graph or curve or diagram that gives for all of those? Alright, even less. We're going to keep shrinking that number down. Alright, cool. So, first thing, what properties are we going to be looking for in blade metal? Anybody want to take a stab at it? That was bad, terrible jokes. Yeah, so anybody, let's hear some thoughts. We keep you guys engaged. Yeah.
Not break.
Not break. Solid. Any other guesses? I know we have a couple material science people in here. Like, come on.
High toughness.
What's up?
High toughness.
High toughness. That's good.
Not brittle.
Not brittle. Yes, we want not brittle. Another word for that is also hardness. But we do want some hardness. So when it comes to our blade metals, here are the primary properties that we're going to be looking at when it comes to our blade metals. We want ductile materials. It needs to be able to absorb an impact without shattering. So that comes to the brittleness. Ductility is typically in juxtaposition to hardness. But you don't want it to be so ductile that it bends when you're striking something with it, or if you drop it on the ground that it just bends all of a sudden. You want it to be hard, and so that's so that you have an edge to your blade while striking. One of the things we did last year, if you ever saw any documentation for it, which we can always show you guys at a later date, they actually made the center of the blade, the core of the blade, more ductile than the edge. And the purpose for that is so that it doesn't shatter when you strike, but the edge is still hard enough to keep that fine sharpness that you can swing through and cut something, not worry about the edge of the blade bending. This is a really big one. It needs to be workable. When it comes to the metals that we're going to be using, we have to be able to work with it. We have to be able to deform the metal without it breaking. So we want to be able to hammer the metal and not have it crack and fall apart. And this, one of the things that we use to look at whether something's workable or not is how large the plastic region is on a stress strain curve. We're going to go into that a little bit more in detail. And the last thing is we want a strong material. There's a reason we don't make these out of ceramics. Some materials are just overall weaker than others in all aspects. So for instance, if you had a pure gold sword versus any type of steel sword, there are some pretty bad steels, but overall gold is just a weaker material, and you can bend it with your hands as opposed to pretty much any steel. Any steel will beat out gold every single time, except for conductivity. But we don't care about that because we're not making power circuits. All right. So going more, talking about workability. So how many of you guys are familiar with a stress strain curve? Okay. So we have a couple people that not quite sure. So when we have the stress strain curve, we have we basically load it into a machine that pulls on the sample at both ends in order to test its tensile strength. And this is the amount of force required and the amount of deformation required until a material breaks. And it generates a graph like this. So we have a region right here in the beginning, that's the elastic zone. That is where if you deform the material, it will go back to its original shape. For most metals, this is not noticeable to the eye. You will not see when a material elastically deforms, unlike for say a rubber band, when that elastically deforms and then it just snaps back to its original shape. There are a couple very cool space metal alloys that have a very large elastic region and that will revert their shape. But for the most part, metals have very small elastic zones compared to other materials such as polymers. And then the thing we're really concerned about is this plastic zone. And this is where we get deformation of the material. And deformation of the material can be things like when we strike it with a hammer, when we put it through a hot roller, anything that's going to change the shape, surface area, that kind of stuff, for the metals. And the larger this zone is, the more you can work with the metal before it'll break from whatever you're doing to it. So if you're not careful and you're using something with a small plastic zone and you put it through the hot roller, there's a chance that it'll snap, it'll develop cracks in it, things of that nature. Or it'll just have a lot of unnecessary strain that could then later on yield failure unless we heat treat it or do something else to reduce the tension in the metal. Poor workability results in cracking, failure, or excessive strain. We want to avoid all of those things. Again, we don't want to waste a ton of material, and so knowing these kinds of things ahead of time can really help with our processing. Also, I forgot to mention, if you guys have any questions at any point about things that we're covering, feel free to ask at any time, and I'll stop and answer a question. All right, cool. So that's workability. Any questions on workability? No? Okay. So next up is the general properties of metals. So these are some other things that we typically look at. So this is going back to toughness, how brittle something is, how ductile something is, or how malleable something is. So toughness, for those of you who don't know, the ability to withstand impact, prevent cracks from propagating, basically keep the material intact. Brittleness is, again, another word for hardness. They're kind of interchangeable. Brittleness is typically referred to in a negative connotation, while hardness is a positive connotation. So if you know someone that studies ceramics, they will say, wow, ceramics have great hardness. And no, they're just brittle and suck. Malleability, it's similar to ductility, but malleability considers only when under compression. And for everything that we do, for the most part, we will be looking at things that are like malleable as opposed to just ductile in general. Ductile is a lot of the times used for more things like when you're extruding a metal, you're making a wire. Malleability is going to be, comes from like hitting with a mallet. So when we're doing compressive actions on the metal, and so a lot of the things we'll do will revolve around compression on a metal to yield some change in dimension. And so this kind of lists some common metals and the rankings for them on these different properties. The top is the best or the highest value, and the bottom is the worst or the lowest value. But these things can all change a lot depending on what we do to those metals, and so we'll talk about that a little bit more as well. So how do we obtain desirable properties with our metals? Specifically for bladesmithing, there's 3 things that we can do in order to change our properties. Does anybody have any ideas what 3 things those might be? Yes?
Heat treatment.
Heat treatment. That is one. It's part of a bigger one, but yes. Anyone else? Got any guesses? No? Okay. You guys are very interactive. So here's the 3 big things that we can do as bladesmiths in order to change the properties of materials. So the 3 big ones are alloying, work hardening, and microstructure control. And like heat treatments are going to go underneath microstructure control. So alloying, I'm sure does anybody not know what an alloy is? Solid. All right, you guys are good. So we can alloy the materials, include other elements, include other metals, in order to create a better metal than what we had to begin with. Because all pure metals are awful. When it comes to everything we do, you never want a pure metal unless it's for aesthetic purposes, because the properties of it are absolute trash. So we can alloy metals with different metals. So an example of that would be bronze. We can also alloy metals with non-metals, and an example of that is steel. So we take iron and we put carbon in it, and now we have steel. We can also put things like chromium in there in order to give it better corrosion resistance. We can also put magnesium or lithium in it to give it, I think that's hardening. It depends on what metal you're putting into what, in terms of properties. You'll learn more about this when you learn the Hume-Rothery rules. But for our purposes, just know that we have those types of alloying abilities. A lot of the times when we get our metals, they're already going to have alloys with them. The only chance that we will have to ever make an alloy would be if we're going to do some casting, in which case we could make like our own bronze or our own brass. That could be a possibility. All right, the second thing, work hardening. So that is basically we create dislocations in a material, and that causes the material to become harder. Have any of you covered that in your classes yet? Yes. Has anyone not covered that in their classes yet? Yeah, because you're an industrial major. So basically, when we have the dislocations in the material, so when we deform a material, it creates dislocations. That's actually the process of how it deforms, is through the creation of dislocations. It allows it to hold different shapes without changing the microstructure of the material, or without terribly changing the microstructure of the material to create new grains or anything. And so dislocations prevent more dislocations from moving. And so, for instance, if you have a carbon atom in your iron, so we have a steel with iron atoms and a carbon atom in it, the carbon atom will keep some dislocations from moving, and if it's not able to move, it's not able to deform, and that increases the hardness of that material. So yeah, work hardening is always caused by the deformation of the material below a certain temperature. Does anyone know what that temperature is at which you will no longer have work hardening? Take a stab. Anyone? 30-10.
Glass transition point.
Nope, but I appreciate the effort. So the glass transition point is going to be more, I feel that's more for polymers. But for metals, it's generally between 0.4 to 0.6 the melting temperature. It depends on the exact metal you're working with, what that exact temperature is. Past that point, and in Kelvin, by the way, because we use absolute temperature scales when we're working with science stuff. So anything above that point, you will have dynamic recovery, in which you are not, the material's not getting any harder because it is hot enough for diffusion to occur, which then reduces strain, caused by the work hardening. And then the last thing that we can do is microstructure control. And so all the materials, all the metals that we work with have their own microstructure. This consists of either the grains themselves, things in the unit cell of the metal, that'll be things like interstitials or vacancies, and that all affects the final properties of our materials. So for those of you that don't know, all like the theoretical values that they calculate for different materials are always going to be different than what the actual values are. Sometimes they're higher, sometimes they're lower, because we have a bunch of things that change the properties: grain boundaries, interstitials, impurities, things like that. So the different size grains affect the property of the metals. Smaller grain sizes are almost always better for everything. The only time you don't want smaller grain sizes is when you're putting things in situations where creep occurs. And creep is when you have something that's under a lot of strain and it's hot. That will cause the material to slowly deform over time and eventually cause failure. But for swords, we don't have to worry about that because we're not going to be working in that hot of an environment with a sword under tension for that long, or compression. And then another thing we can do is the inclusion of different phases or precipitates inside the metal. So for some metal combinations, a lot of alloys, there will be multi-phase regions where you have one phase of one metal and then another phase of the same metal but different composition, and those change the microstructure, those change the properties. And you can also have precipitates of other phases or sometimes of impurities. So for instance, a lot of the times something that happens in metals is the creation of carbides along grain boundaries, which then changes the properties of the metal. And that's another thing that we have to look out for when we're working with metals, because we'll be putting it into a coal furnace. And so we could get more carbon content than we wanted, and we could get carbide precipitates out in our metal, depending on how long we're going to have it in there and how hot we're going to be making our material. All right, the next thing we're going to do is we're going to look at two phase diagram examples. that are going to be important to us. You probably have seen these before. I hope you've seen these before. If not, your teacher's garbage. So this is the one for, I believe this is bronze. Yeah, this is the bronze phase diagram. Copper zinc is bronze, copper tin is brass, so that you all know. The reason that we're looking at bronze instead of brass, even though we use brass more often, is brass is a very complicated. Yeah.
Copper tin is bronze.
Never mind.
Opposite.
Apologies, opposite way around. The reason we're looking at brass, then screw bronze. The reason we look at the brass one is because this is very simple for a phase diagram. And so anyway, real quick, how many of you guys haven't seen a phase diagram before? One? Some people don't know how to read it. Okay, so basically this varies composition and temperature. For those of you watching online, varies composition, varies temperature. And that's how we can calculate what phases are going to form, at what temperature they'll form, and what we should expect when we have different mixes of different elements. Typically a phase diagram only contains the composition of 2 elements. There are ones with more, and there are phase diagrams as well that have preset values, so that you have, for instance, like some sort of steel with like chrome inclusions and a fixed amount, and then you vary carbon content. Things like that. A phase diagram will show several phases. For those of you that have some difficulty reading phase diagrams, because I discovered up until junior year, a lot of people have trouble reading phase diagrams. We have a bunch of different phases. So there's an alpha phase, beta phase, gamma phase, liquid phase, epsilon phase. These are all single phase regions. So if you have that composition and it's in that temperature range, you will have just that. It will be entirely that if you let it reach equilibrium. So if you bring it up to this temperature, it'll be liquid, lower it down to here, and hold it for a while, it'll become an epsilon phase. And then anything that doesn't have a label, but there are 2 single labels around it, that is a 2-phase region. So right here we'll have both beta and gamma in a 2-phase region. That is important to recognize. If you're an MSE, you will have this on an exam at some point, so you might as well learn it now instead of having to worry about it later. A lot of people fail 30-10 exams because of that stuff, at least in my class. I don't know about your guys'. And so there's a bunch of stuff that goes more in depth on the 2-phase regions and stuff like that, but we don't really need to worry about that as much because we're going to be working a lot of the time with fixed concentrations. These are mostly important if we're going to do any castings, so you guys know about that. And also so that if you go and look up, for instance, if we're working with, for some reason, just plain steel that's 0.5% carbon, you know at what temperatures it's going to transition to a different phase. And we're actually going to turn over and look at that right now. This is the one for, this is the steel phase diagram. So it's iron carbon. And it's important, so let's say we have some steel and it's 1 weight percent carbon, right? We need to know at what temperature it's going to start to transition to different phases for when we do heat treatments, when we're working with it, and when it's also going to melt. So for instance, if we're working with 1 weight percent steel, right, at about, I would say about 1300 C, right, we're going to start to get a liquid forming. And so we want to avoid things like that. And so just being able to look at the phase diagram and recognize when different things will happen is really important for metalworking, and especially when we do heat treatments. And we're going to look at the time temperature transition graph too, which goes along with how we're going to heat treat metals in order to get different things. So there's a couple of important points on this graph, or on this phase diagram, that we might end up using at some point, depending on what the blade team decides to do. There's a couple of eutectic points on this one. I think this one only has 1, thankfully, which is right about here. This is for cast iron, and I think there's technically one right here, but that's a different type of phase. Anyways, so when we have eutectic points or a transition between 2 different phase regions, we can get different structures which greatly affect the properties of that metal. Anytime you have two different phases. So like right here we have perlite. That's going to have significantly different properties than, for instance, just regular austenitic steel. And the presence of these two phases is super important. And we can, if we were to get, for instance, if we ordered perlite steel, right, and then we heat treat it, it's possible to lose the thing that makes it perlite through heat treatment. So that's also something that's important to note for phase diagrams, is knowing when those types of transitions are going to occur, when we're going to lose or gain things like that, and things to look out for. Does anybody have a question about phase diagrams? Basically, you just need to know how to read a straight line up and down for a temperature. No. Okay, so now we're going to look at the more important thing, which is a time temperature transition graph. There's a couple of different names for it. Just know that it'll have something to do with time and temperature. Most commonly, it's a TTT graph. There's a CTT graph, which is a continuous time temperature curve. And there's a bunch of variations on that. You should see them at some point in your classes. But this is one of the biggest things that we're going to use for heat treatment of all of our metals, and it will affect things the greatest. And this is what we did when we write our paper. A lot of it is going to be based on a time temperature transition graph for the steel that we're going to be using, or what we predict is going to happen to the steel. And that's what we get graded on for our presentation. So it's a good thing to do. So we use this graph to determine heat treatment processes and cooling rates. So for instance, if we're doing cast bronze as well, depending on how long we cool it, could depend on what phases are present. The axes for this are time and temperature, it's in the name. And then the reasons that it's important when it comes to time of cooling and heat treatment is because that determines how much diffusion is allowed to occur in the metal. And if it's allowed to diffuse long enough, you'll get an entire single phase, depending on where you are in the composition curve, or it'll devolve into something else that we might not want. So the different phases take different amounts of time to form. This is super important for solid to solid transitions, which is what we work with a lot, because we're not going to be melting this steel down into a liquid. We'll usually start with pre-bought steel, heat it up to some set temperature, cool it back down in a certain amount of time in order to try to get a certain phase. So it never turns into a liquid, and we're always working with solid to solid transitions. So if we want to get some different phase of steel, we have to worry about the solid-solid transitions, and that's where diffusion is super important. Yeah, and if you rapidly cool something based on this time transition curve, right, it will freeze that that phase at that point in time. So if we went back to the phase diagram for steel, right? So notice we have austenitic steel here, and then we have ferrite steel down here. If you just let it cool, I think air temperature should do it, room temperature. If you let austenitic steel cool at room temperature down to ferrite steel, you'll get ferrite steel. But if you take austenitic steel and then immediately quench it in water, you can still preserve some of the austenite structure, and that'll take a lot longer at room temperature to diffuse into ferrite steel. Yeah, and the time on the graph is an exponential time. You can see that here, where it starts at 0.1 and goes up to 10 to the power of 6. The longer amount you hold your time, or the longer you have it at a certain time, the longer it'll take to get that tiny little bit of material to change into the phase you're looking for. So this is a super simplified version of the steel TTT graph. It's missing a couple of things on it, but for our purposes, this is good enough to learn with. Basically, what happens is you can look at where you're starting from, what your starting temperature is, and then you see the different phases around the time temperature transition graph. If you want to have a certain amount of a set phase, you would lower it to that temperature, and then you would hold it at that temperature in order to allow that phase to develop. And then once you've acquired whatever you want it to be, depending on how much time it would take, you can then quench it or lower the temperature to a different phase, allow a different phase to form, and then try again at a different phase. This is primarily for generating these structures. a continuous time transition graph, which I don't have an example of at the moment. It's a little bit more complex, but that's more for if you're taking it and you're working with it at, let's say, 800 degrees Celsius, and then you want to lower it to 400 degrees Celsius, and then have a cooling rate from there, then you would use a CTT diagram over a TTT diagram. It's a minute difference, but it matters. And so one of the things we try to do a lot is we try to get harder phases in certain regions by either heat treating it separately or by quenching it and then heat treating it later. So for instance, a thing that we want a lot of the times is martensite, because martensite is super hard. And so you would lower it down to a martensite temperature and then quench it. The CTT diagram, a little bit better. But let's say we wanted like gamma and bainite, right? You would make sure that the steel is in that temperature range and then holds for a long enough period of time. And then once you have the desired amount, which is kind of hard to calculate with this, you kind of just wait a little bit. But you would then quench it at a set period of time in order to achieve that phase. So one of the things you'll do a lot is you'll change the rate at which you cool in order to maximize the amount of that phase that you're generating. So for instance, if you're going to go to try to get gamma plus bainite, right, you're going to have it at 500 degrees, but you're not going to want to cool instantly. You're going to want to try to cool along that curve in order to maintain that structure or develop it the best. And so then we'll use different quenchants, like we'll use water, we'll use oil, you can use air. All of those have different cooling rates for the different metals we're working with. And that will determine what phases we have based on a time temperature transition graph or a continuous time transition graph. So yeah, so that is my short lecture on metallurgy. The next lecture is going to include things that we are going to actually physically work with, the processes that we'll use, so things like hot rolling, things like hammering, forging, casting, the physical processes themselves. We'll go through all of those, and then after that we'll be able to work on creating like a plan of action for how we're going to take our like Walmart knife and make it, let's say, whatever you guys want to do. If you want to make it harder, if you want to make it softer, it's up to you guys. Typically those are the two that we would do. You can also try to just get a very specific phase. So for instance, if you want to take your knife and make it all into austenitic steel, we could try to do that as well. So yeah, any questions? Yes.
So for the TTT graph,
yes,
is the time on the bottom, is that how long you have to hold it for?
So this is not the time you hold it for. This is the time that is occurring. This is once you've started it. You can figure out how long you have to hold it for by measuring between the intervals. So like, let's say you're going from here to here, right? And because you want to get gamma and bainite, then you would just measure the time difference there, down here.
And that's how long you have to hold it.
And that's how long you should hold it for. The next lecture will also go through a continuous transition curve, because I realize that this one doesn't really show it as well. And we'll do a couple of examples with that, because it's good practice. But I wanted to introduce you guys to this concept of the time temperature transition curve, because it's usually like a 5-minute point in a materials class. But these end up being very important. So yeah, any other questions? Yes?
Can you explain the difference between stress and strain?
Oh, sure. So stress is when you're having some applied force on the material. It can be either in compression or tension. So like I'm leaning on this desk, and then I'm putting this leg of the desk in compression, and I'm putting stress on that material. So the wood is in a stress state right now. If I were to pull up, right, then you have gravity pulling the bottom half down, I'm pulling the other half up. This is now in tension, and that's also stress. When we have our stress strain curves, those are typically always done in tension. There's a compression one, but we don't refer to those as the generic stress strain curve. Those are compression stress strain curve. And then strain is the deformation that the material takes. So if we have a piece of metal and we put it under stress and then it changes its length, that is strain on the material, and that's how we measure that. is the change in length of that material. Strain, more vaguely, is the energy in the material that is caused by deformation. So it can be caused by deformation, it can be caused by certain production, so certain cooling can cause inherent strain in the material. So for instance, if you take, let's say like a U-shaped piece of metal, right? And you have it at a very, very, very high temperature, very close to the melting point, and then you dip half of it in water, right? That's going to contract really quickly and freeze in a certain phase, while the parts outside the water, if it's not super thermally conductive, will cool at a different rate, and you'll have inherent strain in the material due to how it formed. Those are the two really big types. We will primarily look at strain caused by deformation forces, as opposed to inherent forces when it's freezing. Except if you're doing castings. If you're doing castings, then it matters a lot because it's possible to break the material through inherent strain in the material when you're letting it cool from a casting. Any other questions? No. All right, cool. Well, thanks for sitting through my lecture, guys. Again, this is going to be posted online. I will post the video. We will post the video as well as the PowerPoint presentation for you guys to refer back to. For everybody that's watching online, if you're watching this, please make sure you pay attention, take a couple notes. There's going to be a second one in which we go over the processes themselves, and then after that, we will work on generating a plan of action for how to heat treat a knife. And that's going to be some hands-on metalworking. So I highly encourage you to watch these if you are going to be working on those processes, and you will most likely have to be at the planning for the process in order to do the hands-on work. Just to be fair to everybody, we have a lot of people, and we can't fit everybody in Dr. Fuchs's lab at the same time. All right, cool. We're good?